Hello everyone, welcome to part 2 of Cracking Vectors. So in today's session we will be learning about the different relationships between a line and a plane, between two planes, how the interaction between a line and a plane creates different angles, how to find those angles, calculate those angles, and much more. So let's get started. So at the very first we have the relationship between a line and a plane. So over here you can see that you're given the equation of the line r is equals to a plus lambda m, where we know that a is the position vector of a point on the line and m is the direction vector multiplied by a constant lambda, and the plane r dot n equals to d in space may be such that, so we have our first scenario where the line is parallel to the plane and lies on the plane. So when a line is parallel to the plane, there are two things that can happen. One, it can lie on the plane, and two, it can not lie on the plane. So when it lies on the plane, it is completely contained within the plane. So then we say that the line is parallel to the plane and lies on the plane, and the conditions for that to happen is that the direction vector of the line is parallel to the plane. That is, so if it is parallel to the plane, obviously the direction vector is perpendicular to the direction vector of the normal. So if we do the dot product of the direction vector of the line, which is m, and the direction vector of the normal, which is n, we end up with 0. And number 2 is that any point on the line lies in the plane. So a dot n equals to d, where a is a point on the line. Moving on to our second scenario. So over here, since it is still parallel to the plane, obviously the first condition as before has to hold. That is, it needs to be perpendicular to the normal. But since it is not contained within the plane, it will not have any point that lies on the plane. That is, a dot n will be unequal to d. Moving on to our third scenario, which is the line is not parallel to the plane. So what is happening is the line is intersecting the plane at an angle. Okay. So the line intersects the plane at a point, that is the point of intersection, which can be obtained by, so we also have a method of obtaining the point of intersection, which is often asked, substituting equation of line into the equation of the plane and solving for lambda, where lambda is equals to d minus a dot n by m dot n. So how did we get this? Let's do a short overview of how that was found. I'll show you how it came. So over here, how did we find this equation that lambda is equals to this one? So how did we get it? So first we had the equation of the line, which is r equals to a plus lambda m, and we had r dot n. We had r dot n is equals to d. So if we substitute the value of r, we end up with, so from here, so finally by algebraic manipulation we get d minus a n divided by lambda m over here. So now since we have understood all that, let's erase it and go back to where we were. Now, our second step will be to substitute the value of lambda into the equation of the line to obtain the coordinates of the point of intersection. So I hope that is clear. We will be moving on to the next part, which is the angle between a line and a plane. So the acute angle between a line r is equal to a plus lambda m and the normal vector n to a plane is given by cos the angle is equals to the dot product of m dot n divided by the magnitude of the direction vector of the line as well as the direction vector of the normal. So if theta is the angle between the line and a plane, then theta is equals to pi by 2 minus uh, phi, and sine theta is equals to cos theta. So the angle theta between a line r is equals to a plus lambda m and a plane is given by, okay, so we get that, right? So over here what we're doing is basically we do not use a formula directly to find this value. Instead what we do is we find the value of cos this one, and depending on the value of cos phi we then decide how to find the value of theta, so which will obviously be pi by 2 minus this angle. However, if this angle comes an obtuse angle, what do we do then? We do that this will be, if this comes to be an obtuse angle, what we do is theta is equals to phi minus pi by 2. So that is another way it can go. So by convention, we take the acute angle to be the angle between the line and the plane because we are looking for an acute angle theta. However, in the question, they might sometimes ask you to find the obtuse angle of theta. So in that case, you might have to do some manipulation over there, but you get the concept, I hope. Moving on to the next part, which is the shortest distance from a line to a plane. So if a line is parallel to a plane, then the shortest distance from the line to the plane is defined as the perpendicular distance from any point on the line to the plane. Okay. So, for example, if the line is contained, so over here we had learned three different scenarios, right? So let's draw it to show you. So we had seen three examples. One was that the line is contained within the plane. So in that case, obviously the perpendicular distance is 0. However, let's say the line is still parallel but it is not contained within the plane. So it is not contained within the plane, so the shortest distance will be this, right? So the distance between the line and the plane, which has to be the perpendicular distance, obviously. So that is the shortest distance. Or we had a third scenario where they were intersecting. So where it was intersecting, so let's say it was like this. So the line came, pierced the plane, and then went back out of the plane. So in that case, since it is intersecting, what is the shortest distance? Obviously, then the shortest distance will be 0. Okay. So relationship between two planes. So it is kind of quite similar to the relationship between two lines. So we know lines can either be parallel or intersecting. Similarly, two planes can be parallel or intersecting. If the two planes are non-parallel, they always intersect in a line. So we know that when two lines intersect, they intersect at a point. When two planes intersect, they intersect at a line. So it goes like this. So first we have a dot. If we stretch the dot in both sides, we get a line. If we stretch the line infinitely from both sides, we get a plane. So when they're intersecting, they keep going back down the orders. So from the plane we get the line, and then if two lines intersect, we get the point. Okay, given the two planes, plane 1 and plane 2, line of intersection of the plane 2 has a direction vector parallel to the normal, cross product of the two normals. Yes, that makes sense, right? Now the angle between two planes. So the acute angle theta between two planes, plane 1 and plane 2, whose equations are given, is the acute angle between their normals vectors n1 and n2. So what we're basically required to find is this angle over here. So for that, what do? We do the um, theta is equals to cos inverse the dot product of the normals divided by the magnitude of the normals. Okay, so we get the cos inverse of the dot product between the unit vectors of both the normals. So that is how we find that angle. Now two planes are perpendicular if n1 dot n2 is equals to 0. We already know that the dot product of anything perpendicular is 0, and the two planes are parallel if n1 is equals to kn2. So if you see one of the normal is basically a multiple of the other, that means that they are parallel. The shortest distance between two planes. The next thing on our agenda is the shortest distance between two planes. If two planes are parallel, the shortest distance between the two planes is the perpendicular distance from a point on one plane to other plane. So over here, what you can see from the diagram is that the planes are parallel. So obviously, the shortest distance is the distance between perpendicular distance between a point from one plane to the point on another plane. So if the planes are not parallel, they will intersect, and thus the shortest distance within the planes will obviously be 0. Now, what we have next is equation of a line parallel to the axial planes. So over here, we had already learned about axial planes in our last video. Here is a short recap for you guys to see. So we can see that axial plane is one that exists only two of the three dimensions, right? So we have a xy axial plane, we have a yz, and then we have a xz axial plane. So now if you're trying to find the equation of a line parallel to an axial plane, what will that be? So, the direction vector is fairly simple, obviously. So for the xy plane, the z is 0. So if the line is parallel to that plane, obviously the 0, now the z's value has to be 0 in the direction vector. So we have z is equals to 0, we have x with a value, we have y with a value, and then we multiply it with a scalar constant, and then we add it because we know that to write the equation of a line we need the position vector of a point, right? So we use the position vector of a point and then we add that. Similarly for the yz plane, again we are adding it with the direction vector, where since it is the yz plane, x will be 0, we have a value of b, we have a value of c. For the xz plane, the value of y is 0 and we have a value of a value of c, which is added again similarly to the position vector. Now, what is the parametric form? So the parametric form is basically where we separate the x, y and z values. Okay, so over here as you can see, if we separate the x values, we will end up with this portion, which is the x1 plus lambda a. If we separate the y values, we will end up with this portion, and finally we have the z portion. So since over here 0 into lambda is still 0, so z is always equals to z1. Now, if we were to form this into a Cartesian form, we will get x minus x1. So over here, what we're doing is, uh, from the parametric equations, if we make lambda the subject, what we are end up with is the Cartesian form. So for example, we have x Okay. So for example, here we have x is equals to x1 plus lambda a, right? So if we have to make lambda the subject from it, then what we will get is x minus x1 divided by a. From the equation of y, if we have to make lambda the subject, what we get is y equals lambda is equals to y minus y1 divided by b. Since there is no lambda in the third equation, which is the equation of z, we are left with z is equals to z1 itself. So now if we equate the values of lambda, what we get? We get x minus x1 divided by a is equals to y minus y1 divided by b. Similarly, if we repeat this process for the parametric forms of the axial planes of the yz plane and then the xz plane, you will end up with this, where now x is equals to x1, now y is equals to y1. Since they're not passing through the x-axis and the y-axis respectively, their values are always 0 in the direction vector, so the position vector always remains. And similarly, if we follow the similar procedure, we get with this. Moving on to our next part, which is the pairs of lines in a three-dimensional space. So the location of two lines L, where R is equals to A1 plus lambda M1, and L2, where R is equals to A2 plus mu M2 in space, may be such that the lines are. So we have four different conditions that might happen. One, they can be parallel and they intersect. So what happens if they are parallel and they intersect? It means they are basically the same line. So L1 is L2. They are not two separate lines, they are the same thing. So how do we test for it? We test that the direction vectors M1 and M2 of the lines are parallel. Okay, that is our very first criteria. And then any point on L1 also needs to lie on L2. Now, for our second criteria, second condition, which is they are parallel and do not intersect. So, what happens here is their direction vectors are again equal, but this time a point on L1 does not lie on L2, as you can see with the diagram itself, right? Now, they are non-parallel and they intersect. What happens then? So, a direction vectors m1 and m2 of the lines are not parallel, so they will not be equal, and unique values of mu and lambda exist. Okay, so you know how for a line you can get three separate equations, right? So for L1, you have value, value, value plus you have lambda, value, value, value. So by the parametric equations, you can separate it into three different parts, right? So you have a part x, you have a part y, and you have a part z. And then you can repeat the same thing for L2 too. Now if we equate the x of L2 with the x of L1, the y of L2 with the y of y1, and the z of L2 with the z of L1, you end up with three different equations. Now if you solve the three equations simultaneously, the values you get of lambda and mu, the values you get of lambda and mu, if they are equal from both the sets of simultaneous equations that you end up with, then unique values of lambda and mu exist, such that a1 plus lambda m1 and a2 plus mu m2 are equal. Okay, So in that case, what will happen? They are not parallel and they intersect. However, say from the three sets of equations you formed, from the three equations, if you formed two sets of simultaneous equations and the values you found of lambda and mu are not equal from both the simultaneous equations, what happens is that they are not parallel, but since unique values of lambda and mu does not exist, a1 plus lambda m1 is not equal to a2 plus mu m2. Okay, so that will be our test. So what do we call this type of lines? We call this skew lines. Okay, we call this skew lines. Now moving on to projections. Note that projections are not in our syllabus, but I have found that doing projections actually quite clears your understanding of when to use the dot product, when to use the cross product, how the different lengths we find to find their diagrammatic representation in our minds and everything. It helps to clear the concept a lot. So I would suggest you guys looking over it, but you cannot. That's also fine. So for our projections, we have explained it using a sum. So here we have a huge sum which states that the line PQ passes through the points P and Q with coordinates given, and Q's coordinates is not too visible, so I will write it again. So the coordinates of Q is 3, 0, 1, right? And then the plane has the equation we are given. So the acute, so first we have to find the acute angle, point of intersection, foot of perpendicular, the position of vector of Q prime, the reflection of Q in the plane. So we have a lot of part questions here which I would ask you to go home and try, since these are fairly conceptual and you should be able to do given the two lectures. However, if you do find difficulties in it, please leave it behind in the comment section and I will solve those for you too. Now, our main concern over here is the last two sections. So to understand projection, we are mainly going to deal with these two sections over here, which is the length of projection of PQ onto the plane and the length of projection PQ onto our normal of the plane. So what do they mean and how do they differ, right? So firstly, to find the projection vector, what do we need to do is, to find the projection vector, the very first thing that we need to do is to find the vector PQ. So by the triangle law, we know that PQ is OQ minus OP. So we have the vector PQ. So now you can do it by either of the two methods. Either is fine. I prefer the first one, but you can choose to do the second one. Now, use the cross product of the projection vector and normal to the plane to find the length of the projection onto the plane. So the length of projection onto the plane is mn, right? We are required to find this part. Mn. So how to find the length of the projection onto mn? So over here I would give one tip. Whenever you see that for a triangle, you know that the side that it is attached to is the adjacent, right? And we always deal with adjacent in what? While in trigonometry, while finding the cos of any angle. So whenever you have to find the cos of any angle, you end up doing the cross product. When you have to find the sine of any angle, because you have to find the length opposite, so that corresponds to the sine of that angle. In that case, what do you have to do? You have to do the dot product. So if you have to find the length of the projection PQ onto the plane, you simply do the cross product of PQ with the unit vector of the normal, right? So if you do the cross product with the unit vector of the normal, you end up with mn, and then To find the magnitude of the projection, you again need to do this. So firstly, okay, I'm sorry guys. Okay. Okay. So the unit vector of the normal. So to find the unit vector of the normal, what do we do first? We take the unit vector, this, and then we divide it by the magnitude of the unit vector. So which will be root over 1 square plus 1 square plus 1 square, which gives us 3. So we do the cross product of that. So before doing the cross product, we take 1 by root 3 outside so that it is easier for our calculation. We finish with our calculation and then we divide it with 1 by root 3. Now how to find the magnitude? We know that to find the magnitude we do root over x square plus y square plus z square, right? And then we end up with our value. Now you can also do it with the IJK system, something which I would not prefer you to do. And then this method is what we call the shoelace method, which you might have learned while finding the area of a matrix and everything. So here you have, but in either ways you will end up with the same answer. Now, if we have to find the projection onto the normal of a plane, we are looking for this part over here now, right? So how do we find that? So as we said that in a triangle, the trick that I use, so this is PQ and this is opposite to PQ, right? So over here, if you consider this, you have to do something such as sine theta to find the value of this angle. So whenever you have to find sine theta, that corresponds to the dot product. If you have to find cos theta, that corresponds to the cross product. So over here we will be doing the dot product. So that is just a trick I use to remember. You can just plain simple remember it without any trick to use, however, which is still fine. So we are doing the dot product of PQ and the unit vector of the normal. So again, for the unit vector of the normal, we are multiplying the direction vector of the normal with the direction vector of the PQ divided by the magnitude of the normal, which leaves us with root 3. And then doing the dot product gives us with 1. So the answer is root 3 by 3. And similarly, again, this step can be done in either this method or the IJK system, anyone which you prefer. So with that, more or less, this was the conceptual part of our videos. I did not rely too much heavily on the formulas and the sums and how did they come and why we do the cross product when and why do we do the dot product when. I just gave you a simple rule to remember but not a logical in-depth analysis of it, because that will be in our next section, which will be the calculations of vector section. So thank you very much everyone. Hope to see you in our next video. Stay tuned.